Good afternoon, everyone. So today we're going to finish up our unit on optimization, and we'll start the next unit, which is on support vector machines. The last thing we learned was about the Armijo method, which is a way of doing gradient descent that also adapts the step size as we go. And there was this little piece of code here, and I discovered there's actually two problems with it. There should be a minus here, and then there should be a squaring there. But after I changed those, surprisingly, the figures looked almost the same. So.
Did you try and extend the screen?
Oh, I'm sorry. There you go. So anyway, so we learned about that. And then we'll just talk about a few other miscellaneous topics in optimization. So until now, we focused on unconstrained optimization, but sometimes there are constraints on our design variables. So let's say if we're talking about a vector W, sometimes you can have equality constraints, which means that there's some function that you can apply to W such that you get 0, or you can have inequality constraints where there's some function you apply to W that makes it lesser than or equal to 0. So these are different things that can happen. You can have a multitude of these different functions. And so there's sort of a framework that you can handle these using, which essentially reformulates this constrained problem. So minimize this cost J such that you have equality constraints or inequality constraints as an unconstrained problem that involves additional design variables. So that's the main approach, is to reformulate it as an unconstrained one. So it goes like this. Let's talk for a second about the case of equality constraints only. So in this case, what you do is rather than, you come up with some new cost that involves W as well as these new parameters lambda. So this is a vector of different lambdas, and you optimize both over W and lambda. And the way that you construct this new cost is you have your old cost J, which only depends on W, and then you add a sum for every one of these different L's you have. You sum over those L's, and you take whatever function that H is, and you multiply that by your new variable lambda L, which is one of these guys. Okay, so basically you have your old cost plus a new term, and then you jointly optimize these over both W and lambda. So the reason this works, it's not too difficult to see, is remember that what we always do in unconstrained optimization is we set the derivatives to 0, right? So we're going to be doing that with derivatives with respect to W as well as with respect to lambda. Well, look at what happens when you take the derivative of this with respect to lambda and you set it to 0. So the only place the lambda appears is right here, right? So when I take the derivative of this with respect to lambda, with lambda L, I just get exactly this, HL. And then I set HL to 0, which is exactly my equality constraint that I started with. So that's why this works. You basically impose this structure so that when you do that gradient zeroing, that you automatically get the constraints that you start with. So once you have this, now you just basically attack this problem in an unconstrained way. And as we'll talk about later, if this has a nice enough structure that you can do that optimization, then basically you can solve that problem. Okay, so is this idea making sense? How to deal with equality constraints? These things are called Lagrange multipliers. Maybe you guys, have you seen this before sometime? Raise your hand if you've seen it before. I'm just kind of curious. Okay, a few people have.
Can you tell us what that might represent in a real scenario?
Yeah, so I mean, these, it could just be just anything really. Like if you say, for example, that all the W's have to add up to 0, like when some are positive, some are negatives, they all have to balance out, then that would basically be you'd have like the ones vector transpose W equals 0, right? Because that ones vector just sums all the terms. So this would be, if that was your only constraint, you would just have capital L equals 1, and this would be your function h of L. Okay, let me give you another example. Let's say that W happens to be a PMF, probability mass function. So in that case, we know that when you sum up all the entries, they have to sum to 1, and they have to be non-negative, for example. So in that case, you would have these things summing to 1, and you would also have W, I think I called it M, so WM, negative WM is less than or equal to 0. And I'm saying, I'm using the less than just to be consistent here. Right, so I would, basically this would be my G of M function, and I would have, however many coefficients I have, that's how many I would have. So then you could optimize a PMF. Yeah, but there's so many different ways that this can manifest in many different applications. So this is just an example. Okay, all right, any other questions? Yeah.
Is this linked to the math assuming like we have a prior belief about our lambda?
I don't think it's directly linked. I mean, in that case, we express our prior belief using an additional cost term, and then we just minimize the sum of them. So I guess it could be linked if we said that we knew our coefficients had to be positive. And there are problems where that's the case. You just, you're looking for the positive parameters W that solve some problem. And so in that case, it's not specific. Well, I guess you could think of it as map, but the way you deal with it is not to add an additional term so much as to add equality constraints. Yeah, so actually like one way this shows up, we'll talk about this more today, is that sometimes when you represent an image on a computer, you assume, if you just have image intensities, those things can never be negative. Right? So 0 is the smallest value, and it can be, maybe the largest value is 1 or 255. And so in that case, you do have constraints. It must not be below 0, it must not be above 255. And if you incorporate these into your problem, you can actually sometimes get a much better reconstruction than without them. Without them, maybe your reconstruction approach gives you negative intensities, or intensities are greater than the brightest possible, and so on. So this can definitely help. Okay. All right, so this is equality constraints. So this is really all I'm going to tell you about them. We'll see this appear in the next chapter, but we won't get into a lot of details. So I'm just explaining this a little bit. It's not going to be a big focus of the course. But it turns out that when you have inequality constraints, the situation is similar. So here's your equality constraints and your inequality constraints. As you can see, now you have some additional variables. We'll call them mu. And so you have to optimize over them as well. And there's a few other conditions that need to be satisfied when doing this optimization, but you can see that it's pretty similar in spirit. You just add this additional term. So I'm not going to get into any more details here because we won't be using this at all, but I just wanted to kind of point it out and maybe inspire your interest if you want to learn more. I'll list some courses that we teach here at Ohio State that can teach you more about this stuff. Okay, so any other questions about constrained optimization? If not, this is all I'm going to say about it. Okay. All right, and let's now talk about convexity. So the reason we care about convexity, and I've mentioned it a number of times, is that when we do gradient descent, we have to worry about whether we have a single minimum, as in the left picture, or multiple minima, as in the right picture, where here you can see one of the minima has a lower value than the other. So we would call this the global minima, and global minimum, we call this the local minimum. And so in this case, if we really want to minimize this function, we would hope to converge to this global minimizer here, but if we run gradient descent and start here, it's going to take us downhill, and we're going to converge here instead. And that might not be a good outcome for us. So we'd like to understand, more systematically what kind of functions yield this nice, easy situation and what kind of functions yield this more difficult situation. And that's essentially what we get with convex functions on the left and non-convex functions on the right. Okay, so the theorem says if the function you're minimizing is convex and you found a local minimizer of f, we know how to do that, right? If it's differentiable, we can set the derivative as 0. Then x is a global minimizer of f. So you don't have to worry about getting stuck in a local minimum. So that's the nice thing about convex functions. It allows us to do things like gradient descent and not really worry about whether we converge to a bad local minimum. Okay, so so basically the convex function, gradient descent converges to a global minimizer and we're happy. So for the next 2 slides, I just want to talk a little bit about how, what is a convex function and how do we check if a function is convex. Okay, so first, before we talk about convex functions, we have to talk about convex sets. Okay, so a set is convex if, and we can just summarize it in words, if the line between any 2 points in the set remains in the set. So like here I have a picture of a convex set where I take these 2 points x and y and I draw a line between them and I check if every point on that line is in the set. And visually you can see that's the case. And you can see that no matter where I choose my 2 points x and y in this set, the line that connects them will also lie completely in the set. Okay, but here on the bottom is a non-convex set where I found a pair of points such that the line between them goes outside the set. So that would be an example of a non-convex set. And of course you can find cases within it where there's no problem, but this statement says that this has to happen for all points in the set for it to be a convex set. Okay, so let's just look at the mathematical statement for a second. So we're calling the set capital D. We're taking any 2 points that are in D, and we're taking a number t, which is going to parameterize how far we are from x to y. And then we're saying that this new point, which is what they call the convex combination of x and y, which is some place along the line from x and y that is a fraction of t from x to y, that new point has to be in D. Okay, so that's what a convex set is. And a lot of the sets we deal with in practice are convex. So, for example, circles, squares, ellipses, those are all convex. If we're looking at the space of n-dimensional vectors, that's a convex set. Hyperplanes in Rn, just basically if like we're in 2 or 3 dimensions and you imagine a plane cutting through and you're living on that plane, that's a convex set. Or half spaces, like if you take some domain and you chop it in half with a plane and you look at what happens on one side of the plane, that's a convex set. And you can write that mathematically as a set of x such that some matrix A times x is less than or equal to some vector b. That gives you a half space. And we've seen some of this stuff in the most recent homework, right? We had problems where you guys had to figure out what is the set of x such that the outcome is positive or something like that. That was giving you, in a lot of cases, a half space. Okay, so these are convex sets. Any questions on convex sets? Okay, so now that we know what convex sets are, we can talk about what a convex function is. So for a convex function, f, so first of all, this is a function returning just a single output. It's not returning multiple outputs, just a single scalar output. So it's convex. Number 1, if its domain D is a convex set. And number 2, if for any 2 points in that domain and a number t, which is once again going to interpolate between them, this holds. And essentially we can paraphrase this as follows. The function on the average between the 2 points is less than or equal to the average of the function on the first point and the function on the second point. So this is averaging on the input side, and this is averaging on the output side. So on the right we have a picture where we have our 2 points. Here's x, here's y. So the domain is just, in this case, it's the real line. And so on one hand, we can look at the average between x and y, and in this case, we're using some number t, which is, according to this picture, it looks like it's maybe about 2/3 of the way from x to y. So this is averaging on the input. On the other hand, you could look at the function at x, the function at y, and then you could average those numbers. So this would be 2/3 of the way between fx and fy, right? And for this particular point, you can see that when you average at the output, that gives you a larger number than when you average at the input and then put that through the function. So essentially what we need is that for any x and y in the domain, that if you look at this convex combination between x and y, the function there is less than or equal to the average of the function at x and the function at y. So it's basically like, you can have this chord above the function, and there needs to be a positive gap there. So that's what it means for the function to be convex. Any questions on this definition? Okay, so that's how we define whether a function is convex, and we can check it using the same definition. And so here's some examples of convex functions. So starting with this simple scalar input case, if you have a scalar linear function that just scales by a and shifts by b, that function is convex. If you extend this to multiple inputs, vector x, and now this is again returning a scalar output, so you have some vector a transpose times x plus b. This is convex for any a and b. You can move on to the case of a quadratic function, quadratic scalar function. So this one is convex if and only if this multiplier on this quadratic term is non-negative. So in that case, the quadratic will be cupped upward. If you make a negative, then it's flipped, and that's actually called a concave function, sort of the opposite of convex. Okay, so other examples of convex function, anytime you have a norm, could be the 2 norm, could be the 1 norm, that's a convex function of its input. We saw those in lasso and ridge. A function f is convex. This is a scalar function if its second derivative exists everywhere and its second derivative is non-negative. So this is certainly the case for this quadratic function, but you can see that allows you to go beyond quadratic functions and see what happens with other polynomial functions or non-polynomial functions, at least when they're scalar. So it's really all about the second derivative, just needing that to be non-negative everywhere. And it gives us a way of extending to the vector case as well. If we have a vector, if x is a vector, then we do the same thing, except we need the multivariate second derivative, which is called the Hessian matrix. This is a matrix of all the derivatives with respect to like x1 and x2, xk and xl. You stack them all in a matrix, and then you need that matrix is positive semi-definite, which is kind of the extension of this from the scalar case to the matrix case. Okay, so that's how you could check if you have a function of multiple variables, whether it's convex anywhere. You could look at this Hessian. Also, we can use these as building blocks. So if you have 2 convex functions, then its sum is convex. So one example of that is when we first saw lasso and ridge, we had RSS. Remember, RSS is basically like something like, you start with something like an addition inside a norm. So that, and we saw that was quadratic from early in the semester. So RSS is convex, and then we added either the L1 or L2 norm, and then we here see that the sum will also be convex. So the nice thing about the lasso and ridge cost functions is they're convex, so if you have some way to to find a local minimum, then you know it's a global minimum. Composition is also convex, although there is one additional requirement that I forgot to write here. The second function needs to be non-decreasing. So if it's convex and non-decreasing, then when you cascade it through those two functions, then that composition is also convex. So so basically the things that we've seen so far in the course that are convex is RSS and regularized versions, multinomial logistic regression, whether we're working with the binary case or the non-binary case, that is also convex. And it stays convex when we add L2 or L1 regularization as well. So a lot of the things we've seen until now are convex, and that's nice because there's many different algorithms we can apply, and we can run those algorithms, and as long as they're well designed, we have confidence that they will eventually converge to the same place. So when you have all these different options in sklearn, some of them are a little bit faster than others, but they should all be giving you the same answers in the end if you run them for long enough. You shouldn't need to worry too much about which algorithm you choose. Okay, so that's all I had to say about convex functions. Are there any questions on convexity? All right. Just a few other comments. So we learned about these Armijo-based methods. One kind of word of caution is that they work really well with convex functions because they're very good at converging to a local minimum without going too far, adjusting the step size so that it goes too far beyond it. But there are cases such that, like in deep learning, we actually have non-convex functions to worry about. And the problem with an Armijo algorithm on that non-convex function is it will try very hard to converge to the nearest local minimum, but maybe that's a bad local minimum and we actually want to jump out of it and converge somewhere else to a much better global minimum or near global minimum. So this Armijo-based stuff is great for convex functions like we've seen before in regression and classification, what we've seen until now, but it's not a cure-all method. We don't want to always use it, especially when we have non-convex functions. And then there's a few other methods just in terms of algorithmic methods, like we talked about gradient descent, where you have a scalar step size. There's an extension of that algorithm where you have a matrix valued step size that is a lot faster per iteration, but the iterations are much more expensive. So sometimes they work better than so-called first-order methods like gradient descent. Sometimes they're just too cumbersome and expensive. But it is something that it's kind of a well-known method and interesting to consider. And another thing that we didn't talk about at all is what happens when the function is not differentiable. In that case, we can't use gradient descent because we might encounter a point for which the gradient doesn't exist. So one example of that would be lasso. So if in lasso one of your parameters is exactly 0, which should happen, right? We want it to do feature selection, so we want it to turn off certain coefficients. But as soon as that happens, the gradient will not exist at that point. And so gradient descent is no longer something we can use. So there is a whole branch of methods to deal with non-differentiable cost functions. And we won't really get into the details in this course, but these are things you would learn if you took some courses on optimization. And the ones we have here in the ECE department is we have an intro course, 5500, which is taught every autumn. It used to be called 5759, but now it's called 5500. And we have a convex optimization course, which is taught in the spring of odd years. So not this spring, but next spring. It used to be called 7100, but now it's called 6500. And then for the case where, like in deep learning, we said we have non-convex functions, we do have a course called Non-Convex Optimization for Machine Learning. It's taught now in spring of even years, 8101. So these are So I think you can see now how important optimization is in machine learning. It's one of the main things we have to wrestle with. And so if you're interested in learning more, I highly recommend these courses. And they're, of course, useful for many, many things you might find yourself doing, even if you're not doing machine learning. Just basic approaches in data science, essentially. Okay, so that's really all I have to say for this unit. Are there any lingering questions about optimization or anything at all? Okay, all right, so let's move on to the next unit. So this unit is called Maximum Margin Classification in the Support Vector Machine. So to start out, we'll just be talking about nothing very, very technical. Let's first talk about the data set we're going to be working with. This is a very famous data set in machine learning. It's called the MNIST digit data set. So this is a data set that has pictures, small pictures. They're 28 by 28, black and grayscale. So they basically have brightnesses between 0 and 255. And they are of digits, handwritten digits from 0 to 9. There are 70,000 examples in the data set. And data was collected by the American Census Bureau in the 1980s. One of their goals at that time was to have automatic mail readers, so that when a mail comes into the post office, a machine can scan the address and can figure out where to send it rather than having a human do that. So, so these are just examples, roughly, I don't know, maybe 15 examples or so of zeros and ones and twos, and you can see there's quite a bit of variety in these examples. Some of them are a little bit difficult. Like if you saw that, it's, I don't know, it looks kind of like a 2, but it also could be something else. Some of them are a little challenging. Some of the 7s start to look like, I don't know, that's kind of weird 7. Maybe you can make it look like a 9 in some cases and so on. So a lot of them are pretty easy for humans to classify, but some of them are actually challenging. Humans don't get 100% on these. So, why is this a popular data set? Well, number one, it's pretty simple. There's just 10 classes. It's not too large. In terms of, the images are relatively small, so you can work with methods without a lot of computational power. But at the same time, it is a practical, real-world data set. It's interesting. You can get a lot of insight playing with it. And widely accessible, many benchmarks. So this is you can get this from the sklearn datasets using this fetch OpenML, and you can then print the shape. You can see there's 70,000 examples of 784 is basically 28 by 28, 28 times 28. So we're going to focus, so the main technical thing we're going to learn in this unit is called the support vector machine. It's a very well-known approach in machine learning. It was sort of the state of the art before deep learning. Question?
So is that 784 features?
Yes, exactly. So we treat each pixel as a feature. Right. Yeah, so this was the state of the art approach before deep learning. It has been eclipsed by deep learning, but here's a Wikipedia page on MNIST that gives a list of examples of different methods. So the very first one is a linear classifier. It's a pairwise linear classifier. So this is not something we learned about, but it's kind of like a weak linear classifier that has an error rate of 7.6%. Some other things we haven't learned, k-nearest neighbors, boosted stumps. So we'll learn about this kind of stuff when we talk about tree-based methods. Random forests, we'll learn about them. But basically, support vector machines are getting about 0.56% error rate. And then these are all versions of neural networks. And you can see like the best one in the table is 0.17. So the whole point here is that 0.56 is actually not too bad, right? It's like a factor of 3 above the best one in the table, which is basically a committee of 20 CNNs where it's like you kind of vote on the output of all these 20. It's much more powerful than if you just have a single one. So so basically SVMs are pretty good. You know, like in the final project, this will be an option for you, and you'll probably see that it performs equally well, if not even better, to a neural network that you design. So anyway, so that's what we're going to learn about in this unit. But before we learn about that, we have to talk a little bit about images and how we work with them in NumPy. So again, these are grayscale images, so that means that every pixel is a value between 0 and 255. So 255 would be the brightest white, 0 is black, and then gray would be some number in between. We can represent them either as matrices or vectors. If we want to visualize them, we definitely want to represent it as a matrix, and we basically want to like plot this matrix. I'll talk about how to do that in a moment. But if we want to work with them in terms of data, it's a little bit easier to think about them as vectors. And then we can use something like multinomial logistic regression. So at that point, what we're going to do is we're just going to stack the first row here, and then the second row will be stacked after it. The third row will be stacked after that. So we're going to stack row-wise. Once we do this, now you can see it looks like all the data sets we've seen until now, where we just have 784 features. So this would just be one row in our big X matrix. And in fact, that's how the data came here. The rows had 784 features, so the data came with this kind of linear representation instead of, or the vector instead of the matrix. But it's very easy. If you want to change it back to the matrix, you just do dot reshape, and you give it the dimensions 28 by 28 in this case, and it gives you this. So it's very easy to go back and forth. So one comment is just be a little careful in that when you look at a lot of books or papers that involve linear algebra that converts between vectors and matrices, the assumption there is that it's always column-wise. So like if this is your matrix X and you want to convert this to a vector, it's assumed that you take the first column and then below that you stack the next column and so on. You get this long column vector. So that's, just to remember, that's not what NumPy does. NumPy actually works row-wise. So just be aware that when you see these things written down, basically with NumPy, you need to put transposes everywhere. If you transpose this matrix, then the first column turns into the first row, and so on. So basically, NumPy is like the standard linear algebra notation, but with everything transposed. Okay. So, so how do we plot things? We can use the matplotlib, which is our standard plotting library that we've seen until now. And basically, the main command we use is imshow. So here's a little function that takes in a vector x. So it takes in this representation here. And now we're always looking at 28 by 28 images. So these numbers are hard-coded here. And the first thing we do is we reshape x into a square matrix. And with imshow, we can plot it. And we can tell it what color map to use. So here we're just using this grayscale. So the largest value is 1. The darkest is black. And we're also disabling the x and y ticks on the plot, so we don't have those because we don't really need them. And so this is our little plot command. So let's see how we can work with this. So if we want to extract the images from this MNIST structure, that would give us X, MNIST data. But remember that each one of these has the label. So like this is labeled with a 7, this is labeled with a 3, with an 8, and so on. So those are what we want to put in Y. So we can get that using mnist.target. We have to be a little careful because I think the value starts as a floating point number, and scikit-learn doesn't like having the labels as floating point. It wants them to be integers. So we just have to recode them basically as integers, 8-bit integers. So that's what we're doing there. Okay, so to make this plot, what we did is we selected 4 random digits. And it is important in this case to randomize things. So, for example, I can't remember exactly how the data is formatted, but it might be the case that all the first tenth of the data sets are all zeros, and then the next are all ones, and the next are all twos. And if you don't shuffle them, and you like pull out the early ones for training and the later ones for testing, then you're just training on like zeros and ones and testing on twos, and it's not going to work at all. So it's important to shuffle. So the way we're doing the shuffling here is we first figure out how many samples are in our database. We know that's 70,000, but here we're just going to extract that number. And we're going to come up with this permutation. This is a vector of where you start out with like 0 through 70,000 minus 1, and then you randomly shuffle everything, and you get a new vector of randomly shuffled indexes called iperm. And here what we're doing is, as we go through the number we're going to plot, which is in this case 4, we're taking the first and then the second and so on element from this random permutation vector. That the value of that number, IND, will tell us the location in the original data set of the image we're going to plot. And then we're going to use this, we're going to make a subplot. So here we're going to make, an array of 4 horizontal, and then we're going to call our plot digit function, and we're going to extract the ith row of our big feature matrix here, and that will be a vector, but as we know, it's going to be reshaped to be a matrix and plotted. Okay, so this is what we got when we ran this 7381. Human could easily classify these, but I don't know. The three is maybe not so easy, but I think we could probably all agree that's a 3. So we might be curious, how well does multinomial logistic regression work, right? Because certainly we can apply that method to this problem. We just have this big matrix where the rows are the features, 784 features and everything. Let's see how it works. So just to keep things running a little bit faster, instead of using the 70,000, we're going to just train and test on 10,000 just to speed things up. If we used a few more samples, probably the results would get a little bit better, but 10,000 is already quite a lot. So there's going to be 10,000 for training, 10,000 for testing. We are going to do a little bit of feature manipulation here. So this is not standardization in the typical sense. When you work with images, you don't want to do standardization like we talked about. Like the way that we talked about it before, what that would mean is you would look at every particular pixel over your entire data set, and then you would subtract the value to make it zero mean, and then try to expand that number to be unit variance. So that would actually fail on this data set. For example, like the top left corner, I'm pretty sure it's going to be black for every image in the data set, meaning 0. So there's no way you can make that unit variance. It's just impossible, right? So, and also, I think you can imagine you wouldn't want to process every pixel independently. If you did that, you would no longer be able to really recognize an image after that kind of standardization. So when we work with images, we don't standardize the usual way. And we're not going to be doing feature selection either. It's not like that was one of our main motivations for standardizing in the first place. However, it could be that some of the algorithms out there don't, they're a little bit sensitive. Maybe there's some parameters like initialization parameters or something that have been selected by the authors of sklearn. And they might not like the fact that the pixel values here are going from 0 to 255. 255 is kind of a big number, and everything is shifted into the positive quadrant, right? So it's like we really want things to be maybe centered around 0 and have a smaller range. How essential that is, I'm not actually sure. I mean, we could do a little experiment, but what we're doing here is basically we're going to divide by the largest value, 255, multiply by 2, which will make the largest value 2, and then subtract 1. And now we know that all of our pixels will be in the range from -1 to 1. Okay, so this is just a little bit of a pre-processing. Again, I don't remember what happens if you don't do this, but this is kind of standard when you work with images between 0 and 255 is is often rescaling them between -1 and 1. Question?
I've seen 0 and 1 as well. Do you know like the difference between that, or?
I think maybe the difference is that 0 to 1 would be a little bit less zero mean. Like this is not going to be perfectly zero mean because we can't guarantee that half the pixels are white and half are black, but this is going to be a little closer to zero mean, and that might work a little bit better in some cases. It's going to depend on exactly which method we're using, but yeah, both would probably work okay. But that's basically just trying to explain what's going on here. So once we standardize, or quote unquote standardize our data, we're doing this. Notice that we're doing this to every pixel. So it's not like some pixels are treated differently. But once we do this, we then can split into training and test. And notice that we're using our iPerm to do the shuffling. Okay. And so now that we have our training and test, we can just go right to sklearn. We can instantiate our logistic regression model. In this case, we chose to do true multinomial logistic regression. We chose this solver, LBFGS, because it's one of the faster ones for this application. We're going to let it run for 500 iterations, and we're going to choose the let's see, I think this is an inverse weight on the L2 regularization to be not, I don't know, maybe a moderate value. So you could play with this and the performance would change a little bit, but anyway, that's what we chose, and we fit logistic regression to this. Depending on your computer, this might take, I don't know, a minute or so. And what we find is that the accuracy is about 90%. Okay, it's not terrible, but probably not so good. If you think about the image I showed you originally, imagine getting making an error 1 out of every 10 of these. Like we would hope for a little bit better. So multinomial logistic regression is, maybe it's working, it's just not working that well. So, and here are some examples of errors that were caused by it. So in this case, the true one was a 9, but MLR estimated 1, or true one is a 4, MLR estimated an 8, or true one was a 9, it estimated 3, true one is 3, it estimated 5. So those are all examples where I think as a human you wouldn't make a mistake on these, but MLR did make a mistake. So, maybe we can try to understand a little bit about what is going wrong with MLR, and then we can try to design a better scheme, and that will be our motivation for this support vector machine. So let's take kind of a close look. Let's think back to what is happening in MLR. Okay, so this is sort of the procedure that we use to classify our test vector X, which in this case we know is a rasterized MNIST image. So this is what we do. For every class hypothesis, and in this case this is going to be, we have 10 of them total, capital K is 10. We're going to design our bias and our BK and our weights WK that classify X as either in K or not in K. That's the kind of one versus rest approach. And then we're going to compute a linear score by doing this inner product between our features and our weights, add the bias, and that gives us a score which is a real number. And then you can say that the next thing you can do is if you want to convert that real number to a probability, you can put it through the softmax. Essentially, that's what the softmax does. It converts a real number to a probability. This probability is somewhere between 0 and 1. The real number is anywhere between infinity and minus infinity. And yeah, so this is the probability that y equals, that the output is in class K, given our feature vector X. And when we look at the softmax, if you want to maximize this over K, that essentially boils down to just choosing the largest ZK. So we have computed one of these ZKs for every class. Then we just look at the largest one, and then the index of that class is the one we report as y hat. So that's how it works. In terms of visualization, we start with our image. we convert this row-wise into 784 dimensional vector. This is where you multiply, so each one of these rows is one of these WKs. So we do this inner product between WK and X. We add the bias, and we get Z. So Z is going to have 10 values, and we can put it through a softmax if you want to convert that to 10 probabilities. But at the end of the day, you just choose the largest value in Z, which is also the largest value in the softmax, or the index of it, and that's what we report out of MLR. Okay, so kind of a review, and you can see that this operation here is really where the weights are being used. Right? That's kind of where you can see what's actually going on. You're sort of doing a pattern match, if you will, between you're multiplying every one of those pixels by each of these weights, and then you're summing them up. Okay, so essentially, if you think about what you would like to happen, this number ZK, where you use the kth bias and the kth weight vector, you want that to be large when X is from class K, and otherwise, if X is not in class K, you want it to be small. Right? So that tells you a lot about what these WKs should be. So intuitively, I would say if you imagine that WK looks like the image that you're trying to, looks like a class K image, then when you do this inner product, you're basically multiplying every pixel of this template times every pixel in your test image and summing them up. Right? So if X is coming from class K, then it should have bright pixels where that digit is. And to make this value large, you want that these also have bright pixels in the same spot. And then when you do that and you sum them up, you get a big value. And that's sort of what happens. Here we're plotting WK, not as a vector, but we're reshaping WK to be a matrix, 28 by 28. And these are the weights, WK, that are learned from 100 training samples. And so this is W0, and you can see, yes, it actually looks quite a bit like a 0 character, right? 0 digit. W1 looks quite a bit like a 1. W2 looks like a 2. W3 looks like a 3. W4 looks kind of like a 4. And so when you look at these pictures, gray is going to be a 0 valued pixel. White are going to be positive pixels. And something darker than gray, like in the middle, that would be a negative pixel. So when you see the negative here, it's kind of like saying, if your X has content, has brightness there, it gives a negative weight to that. It says, well, it's probably not going to be in class 0, right? So this is like, in class 0, these are the pixels that should not be lit up. These ones, it's kind of neutral about, because those pixels are black in X for any class. And then for a 0, these are the bright pixels, so you hope that those are bright. Right? So that we can kind of understand the weights just by looking at them. Okay. So it's kind of making sense? Okay. Well, here's the problem, is when we do this with 10,000 training samples, all of a sudden, the weights start to look really crazy. It becomes really difficult to see the characters. You can kind of see a 0 here, and kind of see a 1, and kind of see a 2, but there's like so much else going on that you can see it's doing kind of crazy stuff. Like it's looking for very specific pixels to be super bright and specific ones to be dark. So yeah, it's you kind of lose this nice behavior that was happening with a few training samples is eventually lost. And it's almost like it's overfitting to the data set. It's really looking at like the brightness of very specific pixels and using that to judge whether the underlying character was a 0 or a 1. And that's why it's making mistakes on some of these. That's why, because the training and the test are a little different. So in the training, maybe there were some pixels in this image that it thought are more from the 1 class than the 9's class. So when you see these pictures, you can understand a bit about where these errors are occurring. All right? So something seems to be working with 100, but then something seems to be going wrong once you have a lot more training samples. It's not that the performance has gotten worse. If you actually look at the performance here, the performance is going to be worse than this performance on both training and test. It's just that, as a way of explaining what's going wrong, I think this can give us some intuition about what's going wrong. We're trying to match all the training examples from every class because there's a lot of variations. There's a lot of different ways people are drawing their zeros. And so we're really focusing on some really very particular details in this particular class of images. All right, so that's kind of the precursor. Are there questions about this little experiment? Okay, so this is our motivation. This is going to hopefully inspire us to do something a little bit different. It's going to take a little while to develop this. It's one of the more mathematical things that we've done this term. So the very first thing to talk about is to come back just to sort of simple geometry and to take a look at what happens in this case, like a simple example where I just have two features. And so let's say that this is a classification problem where I have one class here, the red class here, this is the blue class. And so when we train a linear classifier, as we know, we get some sort of decision boundary that is also linear. Right? We learned that in Unit 5. And in particular, when you look at the points right along the decision boundary, we know that they satisfy this equation. So for all the x along the boundary, you have that b plus x transpose w equals 0. Okay, so here, b and w are some weights that we've fixed through training, and then this boundary has this particular equation here. Another way we can think about the decision boundary is that the z you get, the value, remember that this is the value of z. Let me make that a little bit smaller. This is the value of z, that z is 0. Okay, and then as you move in one direction, perpendicular to the boundary, z will get larger. In the other direction, z will get smaller. The particular direction you have to travel will depend on the sign of these w terms and so on, but that's basically how it works. So here, this is what we call hyperplane. It's basically, hyperplane is the idea is it's something that splits a space in half. So here in 2 dimensions, a hyperplane is a line, because that splits it in half. If we were working in 3 dimensions, a hyperplane would be a 2-dimensional plane, because that will split the space in half. And in higher dimensions, it's difficult for us humans to visualize it, but it turns out that the geometry is all the same, and it's enough to visualize what happens in 2 or 3 dimensions. That tells us everything we need to know about what's happening in the higher dimensions, which is nice. Okay, so this is our hyperplane equation, which is sort of one of the pillars of our geometric analysis. Now here's the next important point, is that the hyperplane is going to be orthogonal to the weight vector w. Okay, so here I'm plotting the weight vector w. I'm starting at the origin, and so the end point here would be w. And notice that there is a right angle between that w and the hyperplane. Okay, so that's one super important property of w, or of the hyperplane, because I guess we've learned what w is, and now the hyperplane is essentially going to be some vector perpendicular to it. And let's understand where that perpendicularity comes from. So notice that for any 2 points on the hyperplane, so whatever 2 points I want to choose, I'll call one of them x1, call the other x2. We know that this equation is solved for both points, right? So if I have a system of 2 equations like this, and I subtract the first or the second from the first, so in other words, I'm saying I have b plus x1 tw equals 0, and then I have b plus x2 transpose w equals 0. Then I can subtract this from this, and that will equal this minus this. right? So when I do that subtraction, the b's cancel out. I get x1 minus x2 transpose and 0 minus 0 is 0. Okay, so just from any 2 points on the hyperplane, I can see that this happens. And now this, you can see x1 minus x2, that is on the hyperplane. Right? So if any two points, if I look at their difference, that is a vector that's lying on the hyperplane. And you can see that this is basically the inner product. So the inner product is, linear algebra speak, how we determine perpendicularity. When that inner product goes to 0, perpendicularity. If it's non-zero, they're not perpendicular. They're not orthogonal. So does this argument make sense? Does this little proof make sense? Or are there any questions? Everybody's good with this? Okay, so we learned this one important thing so far, that this guy is perpendicular to the hyperplane. So I think this is a good place to stop for today. We're going to go a little bit deeper, and we're going to start to talk about, given any training point, how far is it from the hyperplane? We'll be able to compute that in terms of the parameters of our model. So, all right, see you guys on Wednesday, and if you have not picked up your midterm, on Friday I brought them here, so you can come up and see me and get it now.